Okay, let's play with vectors geometrically. Let's say we've got this guy here that is vector v, and this guy here, let's call him vector w. Let's make him a little bit longer. Say we want to do v plus w. Well, we use what's called the tip-to-tail method. We draw a copy of v. Remember, vectors can be moved around. I can move this around, I can make a copy of it, it's still the same vector, it still points in the same direction, and it still has the same length. Then I put a copy of w at the end of v. So I put the initial point of w at the terminal point of v. Then my resultant vector starts at the beginning and ends at the end. So the third side of our triangle here will be the vector v plus w. So that starts at the initial point of v and ends at the terminal point of w. Now, what if we wanted to do it the other way? Is this commutative? Is w plus v the same thing? Now we would start with a copy of w. At the end of w, put a copy of v. And we start at the beginning and end at the end. So this side over here would be the resultant vector, v plus w. Now the triangles might not look the same, but look at this resultant vector. That guy right there versus that guy right there. Those are the same. So yes, vector addition is commutative. Order doesn't matter. Okay, what if we wanted to do scalar multiplication? What if I wanted 2v? 2v means take v, still going to point in the same direction. A scalar doesn't change our direction, it only changes our magnitude. So now 2v is going to look just like v, but be twice as long. So there would be 2v. Same direction, but now my magnitude is double. What if I wanted negative v? Negative v points anti-parallel to v, meaning still follows along the same line, still has the same magnitude, but now it points in the opposite direction. So negative v points that way. So using that idea, how would we do v minus w? V minus w means draw a copy of v, and then at the end, draw a copy of negative w. W points this way, so negative w would point up that way. Start at the beginning and end at the end. This side over here would be the resultant vector, v minus w. Okay, is that commutative? Notice that points up. What if we wanted w minus v? Now we would start with a copy of w. Here's w. At the end of w, I would put a copy over here, right here at the tip, or at the end, at the terminal point. Put a copy of negative v. Regular old v goes that way. Negative v would go in the opposite direction. So here's negative v. Start at the beginning and end at the end. This side over here pointing down is the vector w minus v. Is that the same as v minus w? No, v minus w pointed up, w minus v points down. These are not the same. Subtraction is never commutative. In fact, v minus w equals the opposite of w minus v. Okay, what if we wanted something like 2v plus 3w? But we just do exactly what we said we're doing. We're going to go 2 v's. So I went in the same direction as v, just twice as long. And then at the end of that, put on 3 copies of W, 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 W. Here's 3W. And then start at the beginning, end at the end. This side down here would be 2V plus 3W. Notice, by the way, always remember this, the magnitude of V plus W is usually not equal to magnitude of V plus magnitude of W. You cannot distribute magnitude. It's called triangle inequality.